Hello, welcome back. Today we're going to actually set something on fire without any sort of kindling with a match or a lighter or anything like that. We're going to set it on fire purely by increasing the pressure and the temperature inside of a chamber. It's really fun, practical demonstration of thermodynamics, heat transfer, and all that good stuff. So in order to do this, what we want to talk about is the pressure and the temperature and the volume of a closed cylinder. So here I have a couple of closed cylinders here. Now you can think of these cylinders being almost like pistons in an engine, right? So you've all heard of a V6 or a V8 engine or something like that. Now those gasoline engines actually have a spark plug in there which generates a spark which ignites the mixture of gas, aerosol gas, with the oxygen to start the ignition, spark plugs. We've all heard of that. But in diesel engines, there are no spark plugs. The ignition happens much in the same way that we're going to demonstrate it today, simply by rapid compression of the gas mixture. So we're going to talk in a whole lot of detail, but the bottom line is if you compress a gas fast enough and enough, you can increase the pressure and also increase the temperature of the gas without actually having any spark igniter device at all. And that can be enough to actually ignite some fuel. In the case of diesel, it's the diesel fuel. Here we're going to use something else. We're going to use cotton. And so without any spark device at all, we can actually achieve ignition. So what I want to do is show you how this works. We have this cylinder chamber here, and you can see that I've actually broken both of these, so I can't do them anymore. I have these cracks at the bottom in both of them, and I think that's because I rammed them too hard in the process of getting all the video for this here. But it's for science, right? So it's all good. What you have here is a cylinder piston here, and you can put a piston here and a cylinder, and you can put some fuel inside. And what we used here was cotton. It works a lot better if you pull the cotton and make it sort of stringy like this. It works a lot better than a giant wad of cotton like this. The more surface area that's exposed, the better. That's the same reason that gas and diesel is aerosolized into millions of tiny droplets. It burns better when there's more surface area exposed to the oxygen there. I also figured out that if you put a little bit of alcohol on this as a little bit of extra fuel, it works a lot better. Instead of alcohol, you could also use this petroleum jelly. This is used to lubricate the shaft here, but also if you put a little bit on the cotton, it helps as well. Now what you have here is a cylinder, and there's two spots for O-rings. You can see them here. Here I've taken them off. And what you do is you put the cotton on the inside, and you rapidly and quickly slam your hand down and allow the piston to compress the gas. And because it's sealed with the O-rings, very little gas leaks out. Of course, a little bit does, very little leaks out. And then you can achieve a very high compression ratio. And as we're going to find out, that also raises the temperature of the gas down there to something like 600 degrees Celsius. And that energy is coming from your hand doing mechanical work, and then we can do the ignition. So let's take a look at it in slow motion and see how it really works. Now, just as a point of comparison, this is the ignition of a butane flame. You can see the sparks are generating a high temperature, which then ignites the butane as it slowly rises from the valve. And you can see the formation of the plasma and then the clear area and the orange flame near the top. The thing to keep in mind here is that usually you need an ignition source of high temperature. That's the flint and the sparks. And then you need the fuel. In this case, it's butane. And then you need oxygen. And only with the ignition source of a high temperature, with these sparks here, will the flame actually form. Here's an incredible ultra close-up shot of the ignition source on a regular lighter. These sparks are somewhere around 3,000 degrees Celsius and generate enough heat to actually ignite the fuel source. Notice that everything is so hot that there's still some residual sparks happening long after the action has finished. Here was my first attempt with the compression device. You can see that I didn't quite slam it hard enough, so I didn't reach full ignition. But as the plunger, the piston, begins to rise and come up, you can clearly see that there was some partial combustion happening as there's now a lot of smoke in the chamber there. All right, let's zoom in a little bit more and see what we can see. The plunger comes down, we don't reach full ignition, but then as the piston begins to rise, you can clearly see the colored smoke there at the bottom there. It looks a little bit cloudy. And notice there's no ignition device, no sparks, no valves, nothing, no spark plugs. This is about as far as I can zoom to get a clear shot. Pay attention to the moment when the piston begins to rise. Look underneath that cotton at the bottom and you'll see the smoke clearly visible. And I can tell you that by just touching the cylinder, picking it up after I did these attempts, they were warm to the touch. All right, here's attempt number 2. Look at the bottom. At the moment I get to the bottom, it's igniting and the flame gets to maximum brightness. Now, as the plunger starts to rise, it starts to cool off the gas very rapidly because the expansion of that gas is starting to do a little bit of work on my hand. It's touching the cylinder. And so the gas temperature goes down. And you can see the formation of the smoke in this example is a lot more prevalent because there was a lot more combustion going on. All right, here is the same clip zoomed in quite a bit, and you can see a lot more of the combustion. It looks like the ignition happens very near to the bottom of the cotton ball, which is where the maximum compression actually is, and the temperature of the gas is the greatest there. But notice that it almost goes out immediately when the plunger starts to rise. There's quite a bit of cotton left that didn't burn because the temperature of the chamber went down so rapidly. All right, this is about as far as I can zoom, and it looks quite incredible as it catches on fire and reaches critical temperature to combust above that kindling temperature without any spark device. It almost looks like sort of like a magic trick of some kind. Here I've saved the best for last. This is a macro lens, extreme zoom, and you can really get on top of that cotton and see how the ignition happens. And you can see that by stringing the cotton out and kind of like pulling on it and getting maximal surface area, that you can see the embers burning kind of in, throughout, and all around the sides. Unfortunately, I tilted the chamber a little bit when I slammed it, so it went out of focus just a little bit, but you can still get the gist of it and see the ignition taking place clearly. Here's the final shot I have for you, extreme close-up macro lens, and you can just see the ignition getting so bright when it reaches the critical kindling temperature there. I don't know about you, but I just think it looks really cool when the piston reaches the bottom of the travel and you can just see the very edges of the cotton begin to glow and then ignite. And then as it reaches maximum compression, you have maximum burning going on without any sparking or any kind of spark plug or anything. And then as the piston backs away, as my hand kind of bounces off the bottom and then the volume gets bigger again, things cool off rapidly and then the burning stops. So that is literally converting energy of my hand into the energy as the temperature of the gas down below. Now there's 3 main ways in which we want to understand this. We have to talk about the volume of the gas that's compressed. We have to talk about the pressure of the gas, and we have to talk about the temperature of the gas. And I want to avoid the tendency to just say, oh yeah, of course it's going to heat up. You compress things, they heat up. Let's not assume anything. Let's think about it from a molecular level. Why do things heat up when they're compressed? And if you go the other way, instead of compress, if you expand something, what happens in that case? We're going to talk about that a little bit too. So in this situation, as I said, you have basically 3 situations happening. You have the volume of the compressed area that's going down as the cylinder travels down, the volume's getting smaller. That's what the down arrow means. At the same time, the pressure is increasing. And I'm going to talk about pressure in just a second, but you can think of the pressure being the force exerted on the walls of the cylinder. And so as the volume gets smaller, you're squeezing everything down. Think about squeezing a balloon or something, and it's pushing back with a more pressure here. So the pressure is going up. And then we obviously saw the fire and all that, so the temperature has to be increasing, and we want to explain all 3 of them. And I'm going to do it first by just talking about the molecular aspects of it, and then we're going to put the ideal gas law down, which you learn in chemistry or physics, and we'll talk a little bit about it. Now, here's the deal. There's no such thing as a real ideal gas, and atmospheric gas here is not an ideal gas either. Ideal gas refers to how the atoms and molecules interact with each other. Do they bounce off perfectly? Do they stick together a little bit? There's lots of things that go into determining if it behaves as an ideal gas. Some gases behave closer to ideal than others. air is not an ideal gas, but it's close enough for us to still talk about it and learn something from it. Just keep in mind, it's not totally ideal. All right? So the bottom line is, why does the volume decrease? Well, that one's pretty obvious. If you have the cylinder here, and if I'm plunging it down, then the bottom of the plunger is getting smaller and smaller. And so because of the mechanical movement, it's going down. So this one I'm just going to put a check mark because it's obvious. We compress it, and so the volume of the gas is decreasing. Okay, so that part is happening. And then here I'm saying, in concert with this happening, the pressure is increasing. Why is that happening? And the main reason that that's happening is that there's more frequent collisions. Right? And what do I mean by collisions? There's a gas inside of this thing, right? And as we squeeze something down and physically make the volume of the gas smaller, then there's the same number of molecules in there. That does not change because nothing can leak out, right? And because at room temperature, the temperature of a gas is basically related to how much kinetic energy each molecule has on average. That's almost exactly the definition in physics. The average kinetic energy of the gas molecules on average, which is related to their speed, that is what we call temperature. That's what we measure as temperature on the outside. And so if the temperature is really the same either way, even if it doesn't go up, just by nature of the fact that you've squeezed it, you made the volume smaller, then these molecules are going to hit the boundary of the wall more often. Because if you have a gigantic room, it takes a while for a gas molecule to get across. But if you have a very small volume, then the collisions with the wall are happening more frequent. And the bouncing off of the molecules, if this is a molecule here, and the bouncing off of the wall is what we feel as the force, and that is what we call the pressure. So because it's a smaller volume, because the collision rate is more, then we have more frequent collisions, right? You can think of, this is like the wall of the chamber here, right? And you have some gas molecule coming in here with some velocity v. And so it hits the wall, and then it bounces off, and goes maybe the other way, just like a mirror. It kind of bounces off at the same angle it comes in like this. And if everything is perfect, elastic collisions mean perfect, no energy goes into the wall or anything, it just goes back into the molecule, then the same speed you come in will be the same speed that you go out. But when it hits the wall, it imparts a force against the wall. This is not happening for one molecule. This is happening for trillions and trillions and trillions of molecules. And so the aggregate of all of them slamming against the wall over and over again, because when they bounce off, they collide with another molecule, and then they go back and hit again, and they go back and hit again and hit again. And this is happening trillions of times a second. And that is what we perceive as pressure. Pressure, if you've forgotten, the concept of pressure is the force exerted on a surface divided by the area. And the units of pressure, in the English units, you might say pounds, the pounds of force per square inch, right? But in the metric system, it might be newtons per square centimeter, or it might be something like that. But it's a unit of force divided by a unit of area. It's how much force is pushing on every square centimeter, square millimeter, square meter, whatever unit system you're working in. And this force is coming directly from the molecules impacting the wall. So if you're impacting the wall more frequently, then you're going to have a higher pressure. If you raise the temperature of the gas so they're hitting the wall faster, then you'll also have more of a force on the wall. And so that's why temperature and pressure are related as well. If you increase the temperature of a gas, then you're increasing the pressure as well. But I want you to keep this mental model here for the pressure being the force divided by an area, because it will help us in just a second, right? Because just to kind of write down what I'm saying here, the pressure is related to the collision rate. And when I say collision rate, I mean the number of collisions per second with the wall, and the energy per collision. If you change either one of them, you can change the pressure. If you make more collisions per second, then the pressure goes up. If you increase the energy for each individual collision, then the pressure goes up. And if you do both of them and increase both of them, then the pressure goes up even more and even faster. So without even considering temperature, the volume goes down of the cylinder, right? We're compressing the cylinder like this. And so we're increasing the pressure just because we're confining the gas to a smaller space and we have more frequent collisions. Now, the final piece of the puzzle is the one that we really want to learn about. is why does the temperature increase? It's very easy for us to say, oh yeah, you compress stuff, the temperature increases. Yeah, you can just say that, but why does it happen? On a molecular level, down to the nuts and bolts, why is it when I decrease the volume of this thing, the temperature increases? And also, in the back of your mind, I want you to think about the following conundrum. You see, when you take this thing and you push on it really slowly, you know, you put it into some kind of like hydraulic press or something, really, really, really slowly, really, really, really slowly like this, right? The volume is still going down and the pressure is still going up, but I'm not making any fire. In fact, if you remember from one of the slow motion clips, I didn't quite push hard enough and a little bit of sort of like smoke happened in there, tiny, tiny bit of combustion, but not enough to see the flame. And then of course, when I did it again a little bit harder, then you could see the actual flame there. So you could just tell that the temperature did not go up as much the first time. And if you take it in the limit, if you take like 100 years to get to the bottom, you'll be compressing it all right. Pressure will be going up, but you won't be getting any temperature increase, or not very much. And we're going to answer that question, but I'm going to put it on the back burner. I want you to hold that in your mind because we are going to answer it by the end here. But just think about it. What is the difference between doing it really slow and then doing it really fast? Why is it doing it fast that makes the temperature go up? That's kind of the central question. Why do you have to do it fast in order to affect this change here? All right. And so to talk about that, we want to focus on the temperature. Now, as I mentioned, what is temperature? It's what we give as a word to the average kinetic energy of the molecules in a gas. And when I say average kinetic energy, that's related to speed. So it's basically related to the speed of the molecules in the gas there. And if you heat something up, quote unquote, and you get a thermometer and you measure a higher temperature, what you're really measuring is a higher average kinetic energy, which means a higher average speed of the molecules in the gas there. And so you can think of kinetic energy being, you know, it's directly related to the speed is what I want you to understand here. What I want you to think about, let's turn the cylinder sideways just so I can draw it a little easier. And I'm going to slam the cylinder this way. So the cylinder, you know, continues on like this, right? The flat base is over here. And, you know, the stuff is down there. The cotton or whatever it is down here. Right? So this whole entire chamber is filled with air, not just a little bit, like trillions and trillions and trillions of molecules. There's nitrogen in here, and there's oxygen in there, and there's carbon dioxide in there, there's water vapor in there, there's all kinds of stuff in here. It's a whole hodgepodge of things going on. And before I push it, before I move it anywhere, I have molecules, and they're going random directions. Some of the molecules are hitting the sidewall, some of the molecules are going this way, some of the molecules are going this way, and some of them are hitting the piston. Right? And there's trillions of them. They're all randomly going in different directions, colliding, bouncing, colliding. And what we're measuring as pressure on the inside of this surface is how many newtons on average of force, or if you're in English units, pounds of force, for every square centimeter or square inch or whatever unit you're working on in that chamber. Okay. Now let's say that let's take the arrows off for right now. I don't want to draw this 2 times. Let's say that I did not push the cylinder first. Everything is just static. In other words, the cylinder is just sitting here and I'm not pushing it, okay? If a molecule travels and hits the end of the piston, what's going to happen? Well, it's going to bounce off, right? And it's going to be going this way. Now, if it's perfectly elastic, as I mentioned before, then the velocity that we come in with is going to be basically the same as the velocity that it goes out with. And what I mean by elastic is we're not losing any energy in deformation. Like if you take a real ball, like an actual tennis ball or a basketball and throw it against a wall, then the basketball compresses and you lose energy just because the ball changes shape. If I take this perfect ping pong ball and throw it hard enough, it'll crush. And then some of the energy goes into crushing it. But these little air molecules, I'm presuming, don't crush and they don't give any energy. You know, they don't jiggle the atoms inside of this. They just purely bounce off. That's called an elastic collision. And nothing is ever really elastic, a collision, right? But we say in physics that in the perfect case, it's elastic collision here, okay? So if it's elastic, it's just going to bounce off. And you're not going to pick up any energy here because it's just like, you know, it's going to bounce off and it's going to come back the other way. But let's change it. Let's say instead of this piston being in a fixed location, now I'm going to slam it. And I'm going to be pushing this way. So the piston is not locked in this position, it's moving, and as the ball comes in, or the molecule comes in, it comes into contact with a moving piston. It's just going to be the same thing as you might expect. This ping pong ball would behave. If my hand is here and I throw it, it's going to bounce off, right? But if my hand is moving like a racket, bam, like this, what's going to happen? Well, I'm going to impart, it's going to come here and my hand is going to impart some energy to the ball. And the velocity of the ball comes off of my hand is going to be greater than it was in the first case. It has to be, because the energy in my hand goes into the molecule speed. And the same thing is happening with this piston, but not just for one molecule, for trillions of them. As I slam it down, I'm compressing it and I'm physically pushing them and physically causing basically a shock wave inside of here, which means I'm compressing and it travels as a wave throughout the thing here. And so that means that in the case of when the piston is moving, the velocity of the molecule is not the same. The velocity of the molecule, I'll draw it on this side, might be much, much bigger. So this might be like V1 and this might be V2, or this could be an initial and this could be V final, right? And so what did we say that the energy was inside of this gas? We said it was related to the kinetic, the temperature was related to the kinetic energy. And if I'm pushing the piston, I'm physically making the molecules bounce off with more velocity than they started with. Because kinetic energy is related to velocity and kinetic energy is related to temperature, then you measure that as an increase in temperature. That's why the temperature increases. It's not just because you're squeezing the volume. It's not just because of that. It's because you're slamming it in such a way that you're imparting the work of your hand, which is in units of energy, in joules, and you're imparting that to the gas, and that's going into the molecular motion of the gas. Okay? And that's increasing the temperature of the gas. So you have three things going on here. The volume is going down because that's obvious as you do that. The pressure is going up just because the container is getting smaller and you have more frequent collisions. And then the temperature is going up because you have more kinetic energy per molecule. And that is not free. You know, people look for free energy machines. That is not free. That is coming from my hand. And my hand is moving because I'm burning chemicals in my body, literally food and water, and I'm not burning water, but I'm burning food. I'm oxidizing food is the right way to talk about it. And we have energy mechanisms in our body that can move our muscles. And the food is not free either because that comes from photosynthesis, if it's plants, from the sun. And the sun is not free either because the sun is fusing elements and releasing energy from nuclei, right? And so it's a whole chain that comes from what I'm talking about all the way into the stars, right? All the energy really ultimately comes from the stars in the end of it here. So that is the main thing I wanted to talk about with this whole thing. That is why when we compress it, the temperature goes up, and that's how we're able to combust it. When you run the numbers and actually do the math on it, this compression ratio that you can achieve from a little device like this is about 15 to 1. In other words, this is the initial volume. The smallest volume I can get is about like this. It's about 15 times reduction in volume. And then you get a much, much larger increase in pressure when you do that. When you compress something like that, the molecules are forced to be close together, they're colliding, they're bouncing off of each other, and the pressure goes up even faster than the volume goes down. And this all leads, as we just mentioned here, with the analogy with hitting the ping pong ball with a racket, to increasing the energy of the molecules, which increases its temperature, and above a certain kindling temperature, it will catch on fire and combust with the oxygen that's in there. And when you run the numbers on this, the gas can get up to somewhere around 600 Celsius. And just to remind you, 100 Celsius is boiling water, so pretty darn hot. Now here's the thing, if you look closely at the slow motion, and I mean really closely, what you will see is that I compress, ignition happens right about here, right? But I have some inertia, so I get a little past it and then I can't push anymore and it begins to bounce back. If I were strong and could hold it here, it would burn as much as it could burn until it cooled off. But because I kind of bounce off and the volume gets big again really quickly, just like when the piston comes down, I'm increasing the temperature of the gas. When it bounces off and the piston allows the volume to get bigger, everything cools off again. And I'm not just talking about cooling off because some time has passed. I'm talking about when it bounces off and goes up, what's happening is you feel the spring effect. Think about squeezing a balloon. You squeeze it and it bounces back. Or a mouse trap. You spring it and it wants to spring back. When I compress the gas, it wants to bounce off. And that's because the pressure on the inside is pushing. So right now, I'm doing work on the gas, increasing the temperature, but then whenever I bounce off, the gas is doing work on the piston. And that work has to come from somewhere. Nothing is free. When I do work on the gas, then that means the temperature of the gas has to increase because the energy has to go somewhere. It goes into the gas. But when the gas expands the cylinder, I'm doing work on the cylinder, and that energy has to come from somewhere. And it comes from the internal energy of the gas, the temperature. And so the temperature has to go down when I'm on the expansion phase. And whenever I'm on the expansion phase, when you look in the slow motion, as soon as I bounce off, the fire begins to go out because the temperature is dropping really fast because of the internal energy going down on the expansion phase. Now, the next thing I want to talk about is I want to talk about why does this only happen when we do it fast? If you were to take this and put the cotton in there and just push really, really, really slowly, I had a machine do it or something, and just hold it here, it wouldn't catch on fire. But when I slam it really hard, it catches on fire. Why? Okay, well, there's a difference in these processes. And the main difference is whenever I do it slow, technically I am imparting a little bit of energy to the gas, even though it's taking a really long time. I am squishing it and I am slowly moving the piston this way. So I'm imparting a little bit of velocity to the molecules, not as much, but over a long period of time, I'm still adding some speed to the particles. So you would think it would heat up. But what happens is if you allow the process to take a really long time, then the increased energy you give the gas has time to go other places through collisions. Has time to conduct its way elsewhere. In other words, if the temperature of the gas increased by a millikelvin or some millicelsius, really, really tiny bit, then if you do it really slow, it has time to collide with other gas molecules and also collide with the walls of the chamber and collide with this wall and also collide with the piston, and it has time to jiggle the molecules of the piston and the wall and radiate it to the air in the outside in the outside environment. In other words, the heat can be transferred when we do it slow enough. It can get out of the gas, is what I'm trying to say. If you compress it, technically you're adding energy to the gas, but if you let it go over a really slow time frame, you give it enough time to get away. So the temperature we don't notice is increasing, and if you do it slow enough, then you can keep the temperature kind of constant. If it took like a year to compress the cylinder, you would never notice a temperature increase in this chamber. But if you increase it really fast, then what happens is you do it so fast that there's not enough time for the heat to go anywhere. And why is there not enough time? Because all heat transfer is due to collisions. It's due to things hitting. That's how heat goes places. I mean, obviously you can have radiation, but that's photons leaving and such. I'm talking about thermal conduction, jiggling of molecules, hitting and colliding with other molecules. And if you do it really, really fast, then there just isn't enough time for the heat to conduct through vibrations, through collisions, to the piston, to the chamber, to the environment. And so all of the energy that you're putting in, it's in the gas and we see it immediately there. And that's why when you go slow, you don't achieve ignition, like I showed in one of the slow-mo clips. But if you go fast, you can contain all of the work that my hand is doing in the internal energy of the gas, and so it can heat up like that. And in science and physics and in chemistry, we have a word for this when the process happens really fast so that no heat can escape. No heat crosses the boundary of the experiment. This is the experiment here, right? You can think of a boundary. When no heat goes in or out, it's called adiabatic or adiabatic, however you want to say it. Adiabatic or adiabatic, it just means that everything either happens so fast that the heat can't go anywhere fast enough, right? Or it's insulated, like you could imagine a piston that was insulated so well that no heat could ever escape. In reality, that's not really the case because heat always can go somewhere, somehow. But in reality, we say if you can insulate it really well, or in this case, if it happens so fast, we call it adiabatic. So when we compress it really fast, we call it an adiabatic process. All right, the last thing I want to say is I really want to tie this to something you might learn in a chemistry or a physics class. You learn about something in chemistry and physics called the ideal gas law, and that is taught to you as P times V is equal to nRT, right? And you learn that the P here is the pressure of the gas, and the V is the volume of the gas. That kind of makes sense. N is related to the number of molecules, so you just call it molecules. It's really the number of moles, but it's related to the number of molecules. This R is just a constant. It's called the ideal gas constant. And then this T is the temperature. And the temperature is not in Celsius, it's in Kelvin, in the Kelvin temperature scale, which is the absolute temperature scale. So if you consider a case when you do this thing really, really slow, right? And then the temperature of the gas stays the same because everything has time to equilibrate. Okay, then the number of moles of the gas or molecules of the gas is the same in the chamber, even if you compress it. The ideal gas constant is a constant. And if you can hold the temperature constant by doing it slow, then that means this is constant, and this is constant. And so what you learn in chemistry is that if all these things on the right are constant, then the pressure and the volume are directly related to each other. If you were to take the volume and have it go down by compressing the cylinder and everything on the right is the same, if this number, this is an equation, it has to be equal. So this is a constant. If this goes down, then the pressure has to go up. Why? Well, you're multiplying these and we're saying it's equal to this. And if this is a constant and the volume goes down, the pressure must go up. All right? The pressure must go up because we're multiplying them and it has to equal the same thing it did before. And if the volume goes up, then the pressure has to go down. If this number gets bigger, this number has to go smaller. So pressure and volume are related to each other. Now it's a little easier when we say the temperature is constant because, you know, we have a lot more variables that are constant. But in the case of slamming this thing down, the temperature obviously changes also. So in our case, it's a little bit different. And I just want to talk a little bit about that. If you allow the temperature to change, if we solve this for temperature, then the temperature will be PV over NR. And when you divide by both of these, PV over NR. And I want to caution you and remind you again, this is not an ideal gas. And this is what we call an adiabatic process when the heat is not allowed to transfer across the boundary. So it's really not great to use the ideal gas law to talk about this, but I still think it's instructive, so we're going to do it anyway. If you take this ideal gas law and you solve for the temperature, the number of moles of the gas or the molecules of the gas is the same, like the whole time we do this. The gas constant is the same. We already said that we are decreasing the volume. We're actually making the volume smaller, which seems to be something that would drive the temperature down, right? Because if you make this number smaller on top, that's going to drive the whole calculation down. So making the volume smaller by itself, you would think would make the temperature get smaller, right? However, at the same time that the volume is going down, the pressure is going up. And we know the temperature rises. So we know that the volume must be going down, but the pressure must be going up. I'll draw with a bigger arrow, a lot more than the volume is going down. And that's why the temperature increases, because pressure is highly nonlinear like that. When you get it really, really, really small and confine all the molecules, the collision rate goes up way more than the volume went down because everything is so small and there's trillions of molecules bouncing off of each other. So the aggregate pressure that you get from that, the pressure rises much, much faster than the volume decreased in the first place. So what's going on, another way to think about it other than the physical description I gave you before, was that the volume did go down, but the pressure rose much, much faster or higher than the volume went down. In other words, the volume ratio was like 15:1, the compression ratio. The pressure went up way more than 15 times in there. And that's the only way that they can multiply together to get you a temperature higher because everything in the bottom is lower, or is constant, I should say. All right, I think that is about all I wanted to say. I think it's practical because it's about engines, and you talk about gas engine that needs a spark and a diesel engine which doesn't. But even if you're not into engines, I just think it's really cool that you can compress something and without any spark device, no flint, no spark plug, no electricity, nothing like that, you can get it to ignite. And I wanted to share with you a physical representation. Why does the temperature go up? It's when you're compressing with a cylinder, you're physically, just like a ping pong paddle hitting a ball, and it is causing the rebound to come off with more velocity when you're doing that compression. And that's why when we begin the expansion process, going the other way, the gas begins to do work on the piston. And so the temperature goes down and the fire goes out. And you can see that in the slow motion. I hope you've enjoyed this. I'd really appreciate for you to drop me a line. Let me know, do you like this kind of deep dive? Do you just want me to show you, I could just show you the slow motion. Yeah, that's cool. How deep do you want me to go? I'd really like to know. And I read every comment. So please let me know what you think, and I'll see you in the next one. Learn anything at mathandscience.com.